So what happens to the capacitive circuits? All right, so we know that in capacitive circuits, capacitor is going to resist the flow of charges because of the gap, obviously. The higher the frequency is, the smaller the capacitive reactance is going to become. All right, that's one way of looking at it. But the next thing is, the electromotive force is what drives the charges in this direction. And then capacitor is going to charge up across the capacitor. It's going to charge up to the voltage difference supplied by the battery or the alternating current generator. So let's take a look at the way the current reacts to the electromotive force within the circuit. All right, so we will explore the relationship between the electromotive force that drives the current, as well as how the current behaves within that circuit. So once again, the capacitor is hooked onto an AC generator. All right, so what drives the current is the AC generator. And then what's going to happen is across the capacitor, it's going to charge up, which means that the voltage difference across the capacitor is going to charge up until the voltage difference matches the voltage supplied by the electromotive force. All right, so this is the maximum voltage value that it's going to be able to attain, and that voltage value is going to keep changing because this is going to charge and discharge and charge and discharge. Is a function of sign. All right, so by using the Kirchhoff's voltage rule, voltage supplied by the battery and the voltage across the capacitor is going to add up to 0. All right, so the algebra is straightforward. All right, so let's come up with, now we have to come up with an expression in terms of how the current is going to behave. So we know that the amount of charge that we can store is going to depend on inside the capacitor, depend on the capacitance and the electromotive force. All right, so the voltage supplied and the voltage across the capacitor will have to be the same. So the voltage across the capacitor can be expressed using this formula. Now let's come up with an expression for the current. The current is how fast, that's the amount of charge moving in the same direction per second, net charge per second, and how fast the charge value changes within the capacitor, how fast you can charge it up or discharge it. The bigger the current is, the faster you're going to be able to charge it up, for example. So, all right, so that is the first differential of charge value that we're looking at, so which means that we have to take the derivative of sine omega t. When you do, it's going to give you omega cosine of omega t. So we'll do a back substitution. And immediately we end up getting a value. We end up getting an expression for the current. All right. So now what does that mean? So this is the electromotive force that's going to drive the current. All right, so it's a sine wave, so that's the maximum value that it's going to have. All right, this is the electromotive force that drives the current, and so this is the voltage that builds up inside the capacitor, or that goes down inside the capacitor, obviously. And then for the current inside the capacitor, we end up getting a cosine wave. All right, so what does that mean? Which means that the current is what's charging up the capacitor. So which means that the current actually, it's being a cosine wave, it just leads the voltage inside the capacitor, because the current is what needs to charge up the capacitor, and that's what it means in essence. All right, so if you're thinking about it, all right, so this is what the voltage is in terms of the capacitor, and then notice that the current is happening before that. So the current is peaking just before the voltage, which means the current needs to charge it up, or the current needs to be taken away, so it has to cause a discharge. And so if it's a capacitive circuit, what that means is, notice that they're no longer in phase. What that means is current actually leads the voltage inside the capacitor. As a phasor diagram, it would draw just like this. All right, so the current is going to be leading the voltage. All right, sine and cosine are 90 degrees off. All right, so the phasors, these are the maximums that they can have. The phasor diagram is just simply going to spin in this direction. Is the projection of current as well as the voltage is going to keep changing along the vertical direction in time. So the current leads voltage by 90 degrees. So that becomes the conclusion. So the current leads voltage by 90 degrees. All right, so now the next question is, this is the maximum current value. All right, so if we go back here. All right, so this is the maximum current value that you're looking at. All right, so speaking of the maximum current value, notice that it's got a frequency term here. Because of the fact that by using Ohm's law, the voltage divided by the resistance is what gives you the current value. All right, so notice that this is your voltage value, so it's this one. And your resistance term, which is the capacitive reactance term, located here. All right, so these two will have to be equal to each other. So when you equate those terms, you end up getting an expression for capacitive reactance, and you know what omega is. Omega is 2 pi f. So do back substitution, you end up getting the capacitive reactance term. All right, so mathematically, this is how this comes about. So capacitive reactance is going to be inversely proportional to frequency. Inductive circuits, inductive reactance has nothing what to do. So inductive reactance, in this case, is going to be directly proportional to the frequency. Let's check to see how the voltage and the current is going to be related to each other. All right, so the voltage is what drives the current. This is the current that's going to be going through the inductor. Across the inductor, there's going to be a voltage. This voltage is going to be the back EMF, which means that it's going to oppose any increase or decrease of the current value. It's going to act in that direction. That's going to. All right, so electromotive force. And there's going to be a voltage drop or voltage across the inductor. And notice that the voltage supplied by the electromotive force, according to the Kirchhoff's voltage rule, voltage drop, voltage supplied by the electromotive force, or the AC generator, and the voltage across the inductor, they will add up to 0. This one's kind of tough to explain because the voltage across the inductor is the voltage that's going to try to oppose the incoming voltage in a sense. All right, and they seem to be voltage supplied and the voltage across the inductor appears to be in phase. All right, they're happening at the same time. So that comes out of the Kirchhoff's voltage rule. All right, so the voltage across the inductor or the voltage of the inductor depends on variation of the current value. And so the change in current times inductor inductance is going to be the voltage value. So we want to check to see how the current is going to behave. So which means that we have to solve this equation for the current. So obviously it's a differential of the current, time differential, time derivative of the current that we're looking at. So which means that number one, just get rid of the dt term by multiplying both sides by dt. And then get rid of solve for I on the left-hand side. All right, so the current value is going to build up to I, the maximum current value. On the right-hand side, though, all right, we got the integral of sine omega t time with respect to time. So, all right, so when we do the integral of it, it's going to give us a negative of the cosine value. All right, so I messed it up a little bit. So let's go back. So when you do the, it gives you the negative of the cosine, obviously omega becomes the denominator. So we do a back substitution back into this. And then the current term becomes this. Okay, now this becomes the cosine of omega t. The term in front of cosine is our current value. It's going to be the maximum current that you can get out of it. And notice that there's a negative sign up front. All right, so we got an expression. What drives, we got an expression for the electromotive force. This is a sine wave. Electromotive force is coming from the generator, AC generator. And here's this reaction of the inductor in terms of generating a current. And that's the cosine wave. Except this cosine is, the current is happening as a reaction of the incoming electromotive force. So that's the cosine wave, but the current in this case, the current is starting here, and it's starting here, and current is reaching its maximum value. All right, the electromotive force is starting here. So the electromotive force is actually leading the current in this case because the current is starting later, according to that. All right, so here's what I'm talking about. This is a tough thing to explain. All right, so this is what the electromotive force does. It's a sine wave. And it's got a maximum value, so it's just going up and down. And here's what the current does. So the current has a later start. It's starting out later in time, in essence, which means that the voltage is leading the current in this case. So it's peaking later. It's the voltage is leading the current in this case. All right, the current is a cosine wave, and the voltage is a sine wave in this case. So if we were to draw the phasor diagram, so this is your voltage, and the voltage is actually leading the current. So the change in voltage is what's responsible for the current which is being generated inside the inductor. So the voltage leads the current in this case, and then leads the current by 90 degrees. So the conclusion is that the voltage leads the current by 90 degrees. All right, so now that we got this expression for the current that we came up with, so this is the maximum current value that you can have, the current amplitude. We also have the Ohm's law like expression regarding the current for an inductor. All right, notice that the X sub L term, which is the inductive reactance term, is in the denominator. So these two terms will be equal to each other. All right, and we know that the omega is 2 pi f. So we do a back substitution. Immediately we realize that the inductive reactance is going to be directly proportional to the frequency. So inductive reactance is directly proportional to frequency. So in this case, voltage is what drives current, but the current happens at a later stage. So which means that the voltage leads the current by 90 degrees. So the voltage leads the current by 90 degrees in terms of the phasor diagram. All right, so in the AC circuits, we know that the voltage in the inductor differs in phase with the voltage in the capacitor by what angle? All right, this is the current leading the voltage leads it. So by what angle? This becomes kind of interesting. It says 180 degrees, so the question is why? All right, this question is kind of misplaced. All right, that question kind of makes sense within the context of RLC circuits. So the question, the way it was stated doesn't make sense. All right, so combine all three into an RLC circuit. Everything is onto an AC generator. So it's the same current that's going to be going through all three elements, except it's going to charge up and discharge the capacitor. So it's the same current. So as you will know, we all know that the current is just going to oscillate up and down while changing direction. All right, so okay, now within the context of this, that multiple choice question makes sense. All right, so the current, the voltage across the inductor is going to lead the current by 90 degrees, and obviously the current charges up the capacitor, so it leads the capacitor by 90 degrees, and as a result, the angle between the voltage of the inductor, phase angle between the voltage of the inductor and the capacitor is going to be 180 degrees. All right, so within that context, that question, now it makes sense. All right, notice that this is a phasor diagram, and these are vectors. Voltage is a vector for the inductor is pointing in the opposite direction as the voltage across the capacitor. So you just sum them up. The voltage across the inductor is going to be larger than the voltage across the capacitor, as it so happens. So this minus that is going to give you a vector in that direction. All right, so that's V sub R. VL minus VC is going to be a small vector right here. All right, so if that's the case, let's take a look at the total voltage of the RLC circuit. In terms of a vector, obviously, looking at the total electromotive force of the circuit. So this is going to be the total value of it. Notice that now we end up forming a triangle. This becomes the hypotenuse.